Hello and welcome to today's lesson on Hooke's law. We'll go through, as part of the lesson, a quick recap on forces. We'll then look at Hooke's law practical, followed by the equation once we've drawn a graph. We'll look at the key terms that come from looking at the graph, and then we'll go through a couple of questions to help with the equation force equals spring constant times extension, which you do need to memorise. So we'll get started by reminding ourselves about forces. Now in front of you, you've got a mass, and you can see it's a mass because it's 20 kilograms. And as a reminder, to calculate the force, it's mass multiplied by gravitational field strength, which on Earth is roughly 10 or 9.8. So in order to find the force of this mass, we would do 20 multiplied by 10, which then gives us a force of 200 newtons. Now sometimes when we refer to mass and force, we might actually use the word weight instead. So we have a weight of 200 newtons or a mass of 20 kilograms. Now when we apply a force to things like a spring, then what you would see is the spring getting shorter. The spring would compress. The spring would start at its original length, but once you've added the weight, it would get shorter. And it's always the difference in length that we're most interested in. So more commonly, you'll end up adding a weight to a spring going downwards, and then you'd see the spring extend. The spring would start at its original length, and then as you add the weight, it gets longer and moves to a new length. The spring has extended, and what we need to find out is how much it is extended by. So this is when it's a good time to look at the practical. So we'd get a ruler or a measuring tape, and we'd measure the original length of the spring. So just here what we can see is that the spring starts at 100 millimetres or 10 centimetres. We add the weight and the spring, unsurprisingly, gets longer. So we have a new length that we need to measure, and we'd do that in the same way. We'd look carefully at the bottom of the spring and the top of the spring and measure it using a ruler. So it's about 132 millimetres or 13.2 centimetres. In another example, here are our two springs. We've got the one on the left, that is the original length, and then one on the right that has extended. So let's just see the original length, so that's 8 centimetres, and it's extended here to about 13.5 centimetres. And as I said earlier, what we're interested in is finding how much the spring has extended by. So it's a case of doing a quick calculation. So 13.5 take away 8, which of course gives us an extension of 5.5 centimetres. Using BBC Bite Size, you'll be able to see the practical in far more detail. It goes through the method step by step of exactly what you need to do in order to get some results. I'll go through it quickly, but if you do go to bit.ly/Hooke's law prac, then that will tell you more written down than I'm going to be able to do so today. A couple of things to point out though when setting up the practical. Notice how the ruler that you're used is on a clamp stand, and that's because you want to make sure the ruler is vertical, just like the mass will be as well, and that's going to avoid errors when reading off the values of your spring. When you read something at an angle, then that's called a parallax error. So in order to get data, what you'll need to do is vary the weight that you're putting onto the spring and consequently measure the new length that it gets to. You'll then need to put the information into a table, and as you can see, I've written the force down here, then the length, and then the key thing is to measure the extension of the spring, how much it's got longer by, or shorter, because you can do the same thing if you're compressing a spring too. So the first thing is the original length, which is 8 centimetres. We then add a bit of force, and that then moves to 24 centimetres. So if we start filling out the table, to start with, when the spring's at its original length, it hasn't extended, so that's 0. To find the extension after adding the first force, you've then got to find the difference between what it ends at and what it started at. So it's 24 take away 8, which is then 16. If we have the rest of the results put in, and again we've got to fill out the column so that we have the extension. Have a go now at writing down those 4 values of what you think there will be. So press pause, and when you're ready, press play, and I'll go through the answers. So as a reminder, it's the length that is the important thing at the beginning. So if we wanted to find out the value for here, we would have to always do the length, take away the original length, so that's 8. So that gives us 32. And again, the next one, the new length, 55, take away the original length, which was 8. 71 minus 8, and 88 minus 8. And that gives us the answers just there. So hopefully you got those right. The key thing is that number there, the original length of the spring. So in science, we like to use the data and turn it into a graph so we can further analyse the data and talk about it. So the next step would be to plot the information with extension on the y-axis and force on the x-axis. Now, in an exam situation, you might be expected to plot a few of those points, but you'll probably be expected to draw the line of best fit. So have a think, and press play again when you're ready, but have a think what that line would look like. So press pause, and when you're ready, press start again. So a line of best fit is one that if it looks like a straight line, it's probably a straight line, and if it looks like a curve, it's probably a curve. If it's a curve, you would draw freehand with half the points above and half the points below the line. If it's a straight line, then you'd absolutely have to use a ruler, and again, half the points above, half the points below. So something like this might be suitable. So I've used a ruler and we've got the points on the line. So that's great, but what happens if we kept adding more and more weights? So we need to go through some key terms shortly, but a spring doesn't keep going on continually. Something strange happens in this area at a certain point. So have a think, what happens if we keep adding weight to our line? And when you're ready, press play. Well, after a while, and it's different for different springs, it depends on the spring that you've got, but after a while, it stops being a straight line and it starts to curve upwards. So in other words, you add a small bit of force and you get a much larger extension. The spring will get longer a lot quicker. And the key terms we need to refer to, there's one here. Any idea what this is called? Well, this is called the limit of proportionality. It's where the graph stops behaving in a straight line. It starts to curve. So up until this point, if you removed the mass or the weight, the spring would carry on getting smaller again back to its original extension. After this point, you're going to start to do something called plastic deformation. the spring no longer behaves like a metal and it starts behaving plastically. In other words, if you change its shape, it carries on being that new shape. And then in the orange part, that's called elastic deformation. So as I said, when you take the weight off, the spring will then go back to its original length. So the grey part of the curve that we have now, the limit of proportionality has been exceeded and extension and force are no longer directly proportional like they were just here. So as I said a minute ago, that's called plastic deformation, or also known as inelastic deformation, just because this point is called elastic deformation. So we'll now start looking at the equation that links all of this together. So force equals spring constant times extension, where force is measured in newtons, spring constant newtons per metre, and extension is in metres. Now the spring constant, that's also known as the stiffness of the spring. The larger the value of the spring constant, that means the spring is stiffer. It's harder to extend or it's harder to compress. Different springs will have different values of the spring constant depending on the job that they do. So things that you don't want to budge very much will have a high value for the spring constant, or if you want things to be very soft, the spring constant will be a lot smaller. So in order to help rearrange the equation, sometimes it's useful to use triangles. Now some people like them, some people less so, but either way, this is how you would do it. So you've got your triangle, let's add in our divide and our multiplication. So spring constant and extension are multiplied. Spring constant has a symbol K, so I'm going to write K just here. Extension can be written with a small e, so they're multiplied together, so that leaves F for our force. So let's use this equation to help us with our graph that we plotted earlier. So we can use it to calculate the spring constant, the stiffness of our spring. So we're going to need to use the graph to get two different values, the extension and the force, so that we can calculate the spring constant. So our equation for that would be K, the spring constant, equals force over extension. So let's find the change in the force. We've got a big triangle just here, so the change is 5 minus 0, because we went up to 5 and we started at 0. And our spring has extended from 0 up to 80 centimetres. But we need to be careful, because if we go back to our equation, we need extension in metres. So 80 centimetres equals 0.8 metres. So for our extension, it's 0.8, take away 0, which then gives us 5 divided by 0.8. And if you put that into a calculator, that gives a spring constant of 6.25 newtons per metre. But you do always have to be careful of the units. The title of this lesson was Hooke's Law, but we haven't actually yet looked at what Hooke's Law says. So Hooke's Law states that the extension of an elastic object is directly proportional to the force applied, provided the limit of proportionality is not exceeded. So have a think. Do our results agree with Hooke's Law? So when you've had a thought, press play again and we'll look at the answer. So to decide upon an answer, whether they agree or not, it's useful to look at the shape of the graph. So if we look at Hooke's Law again, the extension of an elastic object. When we talk about an elastic object, it's like an elastic band. You stretch it and it goes back to its original length. Something behaves elastically. So a spring, as we said, when you apply a weight, you let go, it will go back to its original length. The spring will bounce to and fro really easily. Directly proportional, well, proportional means straight line. Directly means through the origin. And then the limit of proportionality, can you remember where that was? Well, that one was about here, because if you remember, after that, it starts to curve upwards. So do our results agree? Yes. So that's because we have a straight line through the origin. So that shows us that it's directly proportional and it's a straight line, so that means that the limit of proportionality has not been exceeded. On to a few questions now, so you'll need a pen, paper and a calculator. Question 1. A spring takes a force of 10 newtons to extend it by 2.5 centimetres. What is the spring constant in newtons per metre? So press pause, have a go at the question, and when you're ready, we'll go through the answers together. The first step is to remember the equation. Force equals spring constant multiplied by extension. Well, we've got the force and we've got the extension. We just need to be careful with the units and the need to rearrange the equation because we need to find the spring constant. For those that like the triangles, F, K, E, so spring constant is force divided by extension. So we know the force is 10 newtons, and because we want newtons per metre, and this is in per centimetre, we need to convert it into metres. So 2.5 centimetres is 0.025 of a metre, and then we can put that into our calculator. So 10 divided by 0.025, so we have a spring constant of 400 and our units newtons per metre. As an add-on to question 1, what force is then needed to extend the same spring by 20 centimetres? So think about what you know already. You know the equation. It's just a case of using the equation again. We've trying to find the force this time. We've got a new extension and we know the spring constant. So have a go, and when you're ready, press play again and we'll go through the answer. So first things first, let's remind ourselves of the equation. So force equals spring constant multiplied by the extension. We're trying to find the force. We know the extension. Again, we need to be careful because we need to convert it into metres, so 0.2. We know the spring constant from the previous part of the question, which is 400. And again, put that into our calculator. 400 multiplied by 0.2 gives us a force of 80 newtons. And on to the final question, question 3. A spring is 12 centimetres long when it is not stretched and 20 centimetres long when a force of 60 newtons is applied. So there's 3 parts to this question that I'd like you to have a go at. What is extension? So what do we mean by extension, but also what's the value of the extension? What is the spring constant in newtons per metre? So be careful with conversions from centimetres into metres. And then the third part, how long would the spring be when 50 newtons is applied? So have a go, and when you're ready, press play again and we'll go through the answers. Okay, what do we mean by extension? Well, that's the difference between the extended length and the original length. So if we were to calculate that, we know that it's ended at 20 centimetres or 20.0 centimetres, and it started at 12. So one take away the other. So the extension is 8 centimetres or 0.08 metres. And then the next part of the question, what is the spring constant in newtons per metre? So hopefully you started with the equation, F equals KE. Then if you needed the triangle to rearrange to find the spring constant K, that's F divided by E. We know the force, 16 newtons. We know the extension in metres, 0.08. And again, we can put that into our calculator, so 16 divided by 0.08. And that gives us a spring constant of 200 newtons per metre. The final part is to find out what happens when you apply a 50 newton force. So F equals KE. It's the same spring, so we know the spring constant is 200. And we're going to multiply that by 50. The final part is to find out how long the spring would be when 50 newtons is applied. So this time we want to find the extension. So that's force divided by the spring constant. So that's 50 divided by our 200 because it's the same spring. And again, we can put that into our calculator if you need to. And then 50 over 200 gives us an extension of 0.25 metres or 25 centimetres. Well, we've now come to the end of the lesson. So as a quick reminder and a quick recap, we looked at forces, the idea that to turn a mass into a force, you multiply by the value of gravity, 9.8. We looked at the practical when we added weights to a spring and we measured the extension. We then applied it with the equation. We looked at key terms, so proportionality and elastic limits, and then we had a go at some questions. So very well done, and see you next time.